All right, folks, let's start. Hello, everyone. This is Dr. Yuzo, ECE 318, Electronic Circuit 1. And today is our 14th lecture. And today we will keep talking about the DC analysis of the Mosfet circuit. And also, by the second half of the lecture, we're going to review the midterm one. Okay, so let's go ahead. Can you guys hear me? Yep. All right, good. Thank you. So here I'm sharing the screen. This is our slides. Well, first of all, the slides number is 11, corresponding to our last lecture, which is 13th lecture. So don't be confused. Okay, so PowerPoint slides here showing number 11. It's correspond to our lecture 13. These two numbers are not exactly synchronous. But hopefully it won't be confused, since in the canvas I'm labeling the date to better for you to better understand which lecture it is referred to. Right? So this is the last lecture slides, and what we are seeing is the procedure, even a generalized procedure for conducting DC analysis for Mosfet circuit. So first of all, we need to find a DC circuit. How to do that? We remove all of the AC sources. And also we need to open all of the capacitors, if any. Because we could have some coupling capacitors, we need to open them to conduct the DC analysis. After having the DC circuits, we go ahead to try to find always these three things. Okay, always these three things: one current, two voltages. Okay, ID, or say IDQ, and VGS and VDS. And of course, depending on N channel or P channel, we might be looking for a VSG or VSD for P channel. Okay, so be careful. The subscript order matters for different type of MOSFET. Okay. And then how to come up with equations? We have a so-called arsenal. Okay. First, you're assuming saturation operation region. Beginning, there's no way for us to be able to tell which operation region it is. So we have to assuming saturation. Therefore, we right away come up with an ID equation. This formula is available in lecture slides number 10, okay, which it means lecture 12, and page 8 and page 12. Respectively for the N channel and P channel. This is one equation, okay, saturation ID current equation. And then IDS equals to ID and IS. They're the same. Drain current equals to source current. And the gate is what? Open. The gate is open circuit. Okay, gate is open circuit. This is very helpful. And also we need some KVLs. First KVL is the VGS or VSG loop KVL. The second KVL is from the top to bottom KVL. It goes through the VDS or VSD pass. And to find the VGS loop KVL, we very likely need a voltage divider goes first to find a voltage at P and voltage at gate. Okay. This is pretty much the circuit analysis stuff. And then based on these depends, we should be able to come up with the VGS, VDS, and ID values. And what you need to do next is we need to check the previous assumption is right or wrong. How to do that checking? So you're comparing your VDS with VDS saturation voltage value. Okay. How to calculate the VDS or VSD saturation voltage? How to calculate these two? Formula available in the slides number 10, page 7, and 11. Again, respectively for N channel and P channel. So if it turns out that the VDS is greater than the saturation voltage, then that means, okay, saturation assumption was correct. Okay, it was correct. Then we are done. And then we are done. It's operating in the saturation region, and then we are ready for the AC small signal analysis. However, if it turned out that the assumption was wrong, we need to do the analysis once again, okay, all over, by applying the non-saturation ID current equation. And this is obviously different from the saturation ID equation up here. And it is also available in slides 10, page 8, and 12. So redo the circuit analysis to find the VDS, VGS, and ID. This is the procedure. And to make it even more handy, I call it handy, but I developed a flowchart. Let's go over it. So the flowchart is trying to presenting basically the logic. The logic. And it might be more helpful than the purely context. So to conduct the DC analysis of MOSFET circuit, what we need to do? First, you need to be careful. It is N channel or P channel because they have completely different two sets of equations to be applied, right? So first thing I suggest you to be careful, or say identify, is N channel or P channel MOSFET. Okay. If it is N channel, of course, we have a workflow here. If P channel, obviously, is going to be on the right-hand side of the dashed line here, right? So let's say if it is N channel. Now, by the way, how to identify N channel or P channel? How to identify this? Anyone remember?
The direction of the current flow.
Very good. Direction of the arrow, basically, okay, which is also the direction of the current flow. N channel means from where to where?
N channel is the current goes into the source.
Into the source from?
Gate.
Gate. Correct. Okay. Josh is correct. Okay. From the circuit symbol, you can tell, or say from the MOSFET circuit symbol, you can tell. The arrow is from gate pointing towards the source. That is N channel. Otherwise, it is P channel. Okay. After knowing is N channel, okay, or P channel, of course. Okay. Two branches. First branch, if it is the N channel, and then we assume it is a saturation operation. Of course, meantime, it means you have already had the proper DC circuit ready. Okay. Eliminate the AC source, replace the caps with the open circuit. And then assuming the saturation operation, go ahead. You have equations. Okay, based on this DC circuit. These are the equations. I'm specifying them instead of pointing to certain page of the which slides. I'm specifying them. Okay, I'm listing them here. First equation, anyone knows what is this first equation is? Anyone knows? No one yet? This the first equation is the saturation ID current equation. Okay. It's a saturation current ID formula. And you just need to copy or say have it ready on your cheat sheet. It's including a parameter k sub n, which is going to be given, and one unknown, which is the voltage, one of the voltages we need to find, VGS. minus VTN. VTN is the threshold voltage of the N-channel MOSFET, right? So this guy going to be given too. VTN is going to be given too. So Kn, VTN is given. And then in this equation, you obviously have one unknown, two unknown. And also be careful, this is a quadratic equation. Okay, you should end up with two roots. Besides, as you know, the gate is open, the drain current equals to source current. And then you need to write a VGS loop KVL. To write this KVL, once again, you probably need to conduct a voltage divider at first place. Voltage divider. To find the voltage at the gate. Then based on that voltage at the gate, generally speaking, it's very, very helpful for your VGS loop KVL. If you find the loop containing the VGS, okay, you can't find a loop without a VGS, then it doesn't make any sense. Call it VGS loop KVL, right? And then you need a KVL, I call it from the top to bottom pass KVL, including the VDS inside of it. Now, these three circles, VGS, VDS, and ID to look for. Generally speaking, these equations are enough for you to find the values, Okay. And of course, according to the basic algebra, you need to check what? Check if the number of equations is equal to number of unknowns. Be very careful. We are not looking for the gain. In the calculation of gain, if you recall, we have a kind of a rule that the number of equations is going to be one less than the number of unknowns. Because we are looking for the gain. Gain equals the ratio between two unknowns. So it's okay to have one less equation than the number of unknowns. However, here in DC analysis, we're really looking for the voltage and the current value rather than the gain value. So the number of equations must be equal to the number of unknowns. Otherwise, you're not able to find any one of them. Does this make sense? Did I make it clear?
Yep.
All right. Thanks, Shay. So this is a tip. Well, this is not required, but this is not required. I mean, in the problem, I won't ask you how many equations you have, how many unknowns you have, right? I won't ask this. This is very useful tip to check to make sure you have enough equations before go ahead to conduct the algebra. Because algebra is time consuming, however, it's not given much credit. You should notice that. You have enough equations and the correct equation, then you obtain the majority of the credits for the problem, okay? Once it is okay, you have same number, and then you can go ahead to conduct the algebra to find, once again, ID, VDS, and VGS. And after obtaining them, what's next? Checking, right? Checking. Yeah, because once again, everything so far is based on what? Assumption up here, right? Of course, you need to check. How to check? Compare VDS value with VDS saturation value. How to find a VDS saturation value? I'm specifying here as well. You don't need to go back to the slides. VDS saturation voltage is equal to the VGS value, whatever you obtain from here, minus the given threshold voltage VTN. This is how you calculate the VDS saturation voltage. You use your VDS value, compare with this saturation voltage value. If it is greater than this, which means, well, of course, if it is p-channel, guess what? Everything remains same, right? Everything remains same. That's why you're seeing symmetrical or say mirrored workflow. The only difference is what? It's not Kn, but Kp. This is not VGS. It's supposed to be VSG. Well, there's a typo here. There's a typo here. It's supposed to be VSG. It's not minus VTN, but plus VTP. The given threshold voltage for P channel is going to be VTP, not VTN. And IG0, IDS equal, ID and IS are equal. And then you are looking for this time VSG loop, KVL. And then you're writing VSD, pass KVL. Find ID, VSD, and VSG. Checking is pretty much comparing your VSD with the VSD saturation voltage. How to calculate the VSD saturation voltage? VSG plus VTP. Okay. And once again, I'm specifying saturation current equations, these two, and excuse me, and the saturation VDS voltage here and here in this workflow. Okay. And keep going. Let's see the checking. Yep, I'm repeating this checking in this page. So to N channel, of course, it might be yes, might be no, right? If it is yes, what do we say? Done. You should smile, which also means we are ready for AC small signal analysis. If it is no, which means VDS is less than the VDS saturation voltage, what does it mean? Your assumption was wrong. Now what do you do? Look at this equation. What is this equation? Anyone knows? This equation is what?
Non-saturated.
Non-saturated ID current. Exactly. Good job, Josh. It's a non-saturation ID equation. Obviously, you can tell it is different from the saturation ID equation. And gate remains open. ID remains equal to IS. And you're still going to do VGS loop and from top to bottom pass KVL. And pretty much do the analysis all over. To find, once again, ID, VDS, and VGS. However, you are coming across the quadratic equation once again, right? So you're going to end up with two IDs, two VDS, and two VGS. But how to tell which one is right? You need to be very careful on this thing. Very careful on this thing. How to tell which one is right? You need to choose the solution which meet the non-saturation condition, which means your VDS must be less than VGS minus VTN. Does it make sense? Logic? Because this branch means, this branch here means no. It is non-saturation, right? So your solution here, how to tell which pair or say which set of solution is right? You need to choose the set meet non-saturation condition, which is VDS less than VGS minus VTN. Something you need to be careful. And of course, since it's non-saturation region, then this branch, what? Has no AC. No further to go. Okay, no further to go. No AC analysis. It is non-saturation region. It's on state. It's a switch. you're not going to have any amplification. Okay, so meaningless to conduct AC small signal analysis. Okay. On the other hand, if it is a P channel, you're checking these. And we also have, yes, it is saturation. Then no, it is non-saturation. For P channel, you have another, of course, ID non-saturation current, non-saturation current. And then same issue here, two sets of solution. You need to choose the set of solution meet the non-saturation condition. Okay. And if so, no further to go. Okay. And no AC analysis you should conduct. No AC. And of course, no AC to go. However, the problem might still ask for ID or VDS and VGS value. From there, you can find ID value, then done. For P channel, same thing. Non-saturation, well, we might still need the ID value. Still asking for the ID value. Still has an ID. The switching on state, of course, on state still have current, so we can find an ID current here. But once again, no AC. Okay, no AC, no further to go. Okay, you're not going to do any AC analysis. Makes no sense. Any questions regarding this workflow? Everything logical? Everything clear? Any concerns? All right, if everything's good, I think we this is where we ended, right? This is where we ended by last lecture. Example 2, and we have find the we find what this is the P channel, right? This is the P channel. P channel, and then based on the workflow and those equations, we found the ID, VSD, and VSG. Okay. Once again, be careful the subscript. Okay, the order is very meaningful. Very meaningful. Okay. It is very meaningful. We got these values, and then what's the next? Checking, right? Checking. You're comparing VSD with VSD saturation voltage. Has anyone done the rest of the work? Any conclusion? Anyone has done the rest of work? No one?
I think I found that it was in the non-saturation region, but I didn't get any further than that.
Okay, that's fair. And so let's go ahead. First, repeating VSD equals to this value, and then you need to find a VSD value. VSD saturation value, I mean, which is according to the formula, you end up with this value. So what do you find? Your VSD is less than VSD saturation boundary. As Shane just mentioned, it is non-saturation. It is non-saturation. Or in other words, the saturation assumption was wrong. It was wrong. So according to the workflow, we need to redo it. Do it over using the non-saturation formula. Using non-saturation ID formula is this. And also be careful, once again, P channel formula. Apply the correct formula. We have quite a bit. Okay, so you need to select the right one. And the other equations, like the from top to bottom KVLs and VSG loop KVL, those remain same. There's no reason to change those things, obviously. You are able to come up with, as I said, what? 2 sets of solutions, 2 sets of VSD, VSG, and ID. And here, first thing we found is VSD value. Of course, 2. Quadratic equation. So which one is right? Which one is wrong? Right? Which one is wrong? Which one is right? We just discussed this, right? We need to choose the set whichever meets the non-saturation, right? Does it make sense? Because now we know it is already non-saturation. So you're choosing the non-saturation one. The other one probably is corresponding to the saturation, which makes no sense. So which one should be the winner? The left one or right one, according to this?
The right one.
Here we go. Because the right one is meaning the non-saturation, because your VSD is less than the saturation voltage boundary. So it's non-saturation. Exactly. It is should be non-saturation. Okay. And from here, you can go ahead, of course. From these routes, you go to the ID. And that's it. Right. This is the solution, complete solution for example 2. And of course, no further AC analysis is needed. If the problem is asking for conduct AC small signal analysis, that's nothing but a tricky question. You should answer no need. Any questions? Any concerns? Is this all right?
Yep.
All right then. This is the example 3. I think, how about I give you guys some time to come up with the DC circuit first, and then I present the solution for DC circuit. And from that DC circuit, you'll go ahead to really come up with equation and conducting the algebra to come up with the values. That's really just to do it. You need to do it, always so. Because you should have a very simple experience that reading and understand the given solution. It's much easier than really correctly conducted. This is the difference from kind of taking lectures and doing the exam. Understanding the given lectures, everything much easier, and then you really do it independently and correctly. So you have to do it. Without doing it, the exam absolutely disaster. Absolutely can only be disaster. Give you guys 40 seconds, I think, enough to come up with the DC circuit first. Go ahead. On your notes, DC circuit goes first. You don't need to wait for me, okay? As if you think you just need 4 seconds to finish the DC circuit, then go ahead for the equations. And here I'm presenting the DC circuit, fairly easy one. In the meantime, we can also easily identify this is what? N channel, right? There's an N channel. There's N channel. Because the equations are different, right? Some equations are different. Then go ahead, just based on the given arsenal. And if you need those formula, let me try to give you those formula as well. Well, no way to present both formula and the. Let me do this. How about that? I'm giving you the formula for N channel. One is saturation current equation, another is the saturation VDS voltage. You go ahead. You really come up with equations as well as the algebra. Let's see how far you're able to go. In the meantime, if you have any questions, you can ask. Okay. When you conduct your analysis, you can ask questions. By checking the number of equations and unknowns, you can know do you have enough equations or not. Once you have enough equations, you can go ahead to conduct the algebra. Here I'm showing the solution here. Everyone can take a look and to see any questions you have. If you're in the middle of the calculation, then try to finalize it. Okay, try to finish it so you can see if you are able to reach these values. This is a quadratic equation, so you're gonna have two roots, yes. However, if one of them is negative, then obviously immediately you can get rid of it. Right? You know, it couldn't be wrong. It couldn't be right. It couldn't be right. Negative value couldn't be right. Everybody in the middle of the calculation, or anyone reach any value? Daniel, where are you at? Okay. Joe, where are you at?
For VGS, I got 3.31.
3.31.
Yeah.
How about the ID VDS?
I got 3.38 milliamp for ID, and I got 3.9 for VDS.
How about equations? Are you having the same equations, or how much different?
I'm having the same equation, yeah.
Same equations? Anyone else get any results to confirm either mine or two's? Drew, where are you at? Hello, Chu? Are you there?
What is it?
No, I'm not talking to you, Chu. I'm talking to Chu.
Oh,
Chu, are you there?
Can you hear me?
Yeah, I can now.
Oh yeah.
Where you at?
I'm still working on it.
Okay. Kevin, where are you at? Okay. Yep, keep working. Let me know. Let me know once you got the results. True has done, and he has some off from my solution here, and I'm waiting for others to confirm either mine or his.
oh, I know what I did wrong. I put 116K, not 166K.
All right. With that corrected, I think you're gonna end up with same values here. But let's wait one more confirmation, and then we can move on. Of course, too, you can go ahead to do the next step, which is checking. You can go ahead. Oh. And also, meantime, any questions regarding the equations? Any questions? Speak out, Daniel. VDS is from past KVL. Oh, the thing is, these first two equations here and here, these two equations can give you ID and VGS. And then you substitute ID into the last past KVL, you can find VDS. So VDS is obtained at last. after VGS and ID. Any other questions? Any thought? All right, let's move on. I think it's long enough. Go ahead to do the checking. From here to go to the checking. And well, I'm presenting the solution here, but hopefully you don't need to check this solution to come up with your own solution in your notes. This part is fairly easy. Okay, you can easily tell the VDS greater than the VDS saturation voltage boundary. Of course, here I'm not even further calculate the saturation voltage because I can tell easily this is absolutely lower than the VDS. So the conclusion matters. Saturation voltage boundary value does not. So in the end, the assumption was correct, and we are done.
Dr. Zhou.
Yep.
So what if it's equal? Do we just apply that to saturated? Or the
Equals to, you mean V
saturated
equals to V? These two are equal.
Yeah. What
Well,
if they're
equal to be honest, should be considered as non-saturation.
unsaturated? Okay.
Non-saturation. Yeah. I never seen that happen before. So
Okay, I was wondering.
yeah, sure. Never seen that happen before. But if equal is not a stable amplifier, actually. So we definitely going to try to avoid that. So therefore, we consider that as a non-saturation. We don't want to use that kind of Mosfet EC circuit for the amplifier circuit. It's not stable. Any other questions? Anything?